I'm going to introduce to you a concept called a security strategy. A security strategy has to do with the thought experiment where a player figures that their opponent, rather than maximizing their own welfare or their own utility, is this demented tormentor and is simply looking to minimize the payoff that the player is going to get. So when player I chooses the strategy SI, player I believes that the objective of player J is to pick the strategy SJ that minimizes player I's utility when player J plays SJ. So again, player I is thinking here that player J, rather than maximizing his own utility, is just out to torment me and minimize my payoff. So what's the worst thing that can happen to me in this type of an environment? So if I'm this paranoid guy, player I, and I think that player J is just out to get me, and all they want to do is torment me, then if I play strategy SI, the worst thing that can happen to me is that I would get the payoff WI of SI, which is this. So if I'm one of these really paranoid people, what I'm going to do, rather than think about what my opponent's going to do and say, okay, I'm rational, and I know my opponent is rational, and they know that I'm rational, and rather than go down that way of thinking about things, what I'm going to do if I'm one of these paranoid people is to say, well, my opponent is out to get me. All they want to do is minimize my utility. So whatever I choose, they're going to just do what they can to reduce my payoff. So my objective then is to maximize my worst case payoff. Right? This is my worst case payoff from playing SI. So I'm going to choose the strategy SI in my strategy set that maximizes my worst case payoff. In other words, just plugging in what this worst case payoff is, it's equivalent to just saying, I'm going to maximize my choice of SI when my opponent is going to minimize their choice of SJ, utility from SI, SJ. This SI that maximizes my minimum utility is what we call a security strategy. So a security strategy maximizes the worst case payoff for player I. If your opponent, rather than being a rational opponent who is looking to maximize their own payoff, is some demented tormentor who is just looking to minimize your payoff, the maximum payoff that you can get is what we call the security payoff. And the way you get that is by playing the security strategy, which is the strategy SI that maximizes your worst case payoff. So it's a solution to this maximization problem. Let's look at an example to fix some of these ideas. In this game, if player 1 plays A, what's the lowest payoff player 1 can get? We look at the two different strategies that player 2 can play, and we see what the lowest payoff is that player 1 can get when he plays A. And we're comparing between 3 and 0. And 0 is smaller than 3, so Y would be the worst thing that player 2 can play from player 1's perspective when player 1 plays A. And so the lowest payoff player 1 can get from playing A is 0. That's denoted by W1 of A. Similarly, if player 1 plays B, the worst payoff he can get when player 2 seeks to minimize player 1's payoff by choosing the strategy X or Y to minimize payoff, player 1's payoff, is when we look at between 6 and 1, 1 is lower, so again it's when player 2 plays Y, and he gets a payoff of 1, so W1 of B is 1. So if we want to know what the security strategy is for player 1, the worst thing that can happen to player 1 should he play strategy A is that he gets 0. The worst thing that can happen to player 1 should he play strategy B is 1. So the security strategy solves the optimization problem where player 1 chooses between A and B in order to maximize her worst case payoff. That means B is 1's security strategy. And because the worst case payoff from B is 1, 1's security payoff is 1. I'll leave it to you as an exercise to verify that 2's security strategy is Y and his security payoff is 3. In defining player I's security strategy, we've restricted attention to pure strategies. Now let's think of the situation where player I might be able to play mixed strategies as well. Player J is still out to get player I, but player I now, instead of only looking at pure strategies, now looks at even mixed strategies. So player I is going to believe that if I decide to randomize according to sigma I, then player J is going to pick SJ that's going to minimize my expected payoff. The solution to this is what we call a max-min strategy. And of course, the payoff that I gets from this max-min strategy is her max-min payoff. Notice that she's only going to get her max-min payoff in expectation. She could, for some of the strategies that she plays with positive probability, end up with a lower payoff than the expected payoff. That is the max-min payoff. What should be obvious to you right now is that delta SI, which is a set of all mixed strategies for player I, includes all pure strategies. Because you could always just play a strategy where you put probability 1 on one particular pure strategy. That means max-min payoff has to be at least as high as your security payoff. Because here, what you're doing is instead of maximizing over just pure strategies, now you're maximizing over randomizations as well. So you have more options to choose from, which means that your payoff can't be any lower. If anything, it could be higher. So the max-min payoff has to be at least as high as the security payoff. Obviously, if we are looking at the notion of a Nash equilibrium, we're assuming that rationality is common knowledge. So not only are players rational, but they also know that the other player is rational, they know that the other player knows that they're rational, and so forth. So if both players are rational, and neither of them is out to torment the other, and they both know that, then these ideas of security strategies and max-min strategies shouldn't really have much relationship to Nash equilibrium for many games. But there's a special set of games where these things are actually very closely related. That's when there are two players, and those two players have preferences over the outcomes of the game that are exactly opposed. And if the preferences are exactly opposed, then my opponent doing what's best for them is in fact doing what's worst for me. So my opponent, by doing what's best for them, would end up being this tormentor of me. So these ideas of max-min strategies and security strategies are quite closely related to Nash equilibria for this special class of games. These games are called strictly competitive games, and a game is strictly competitive if for every pair of profiles of strategies, S and S prime, whenever player 1 thinks that the outcome when the profile is S is better than the outcome when the profile is S prime. In other words, if the payoff from the strategy profile S is higher than the payoff from the strategy profile S prime for player 1, it has to be that the payoff for player 2 is lower from strategy profile S than it is from strategy profile S prime. In other words, player 2 prefers the outcome that happens when the strategy profile is S prime than the one that happens when the strategy profile is S. This is for two-player games, just to be clear. Whenever you define a new concept, it's always instructive to first look at an example of something that's not what you just defined. So let's first write down an example of a game that's not a strictly competitive game. This coordination game that we saw earlier, where the two players have to decide which side they want to go on, and they both get a higher payoff from matching than they do from not matching, means that they both have the same preferences over whether they match or they don't match. LL gives both of them a higher payoff than LR. So U1 of LL is higher than U1 of LR, and U2 of LL is higher than U2 of LR. So this is not a strictly competitive game. A good example of a strictly competitive game is the matching pennies game. Every outcome in the matching pennies game has a winner and a loser. So if they match, player 1 wins. If they mismatch, player 2 wins. Of course, when player 1 wins, player 2 loses, and if player 2 wins, player 1 loses. So given this setup for the outcomes, if player 1 prefers one outcome to another, then player 2 has to have the reverse preferences. So this is very clearly a competitive game. Let's look at yet another example. This is the game that we saw earlier. Let's compare, for example, this outcome and this outcome. Player 1 prefers AX to BY. Player 2 prefers BY to AX. You can take any pair of strategy profiles and you'll find that there's the same relationship. So this game that we saw a little while ago is an example of a strictly competitive game. Matching pennies actually had an additional feature other than being a strictly competitive game. If we go back to that game, we see that player 1's gain is player 2's loss, and player one's loss is player two's gain. This other game that we saw doesn't have that property. We call games that have the special property that we just described for matching pennies, we call these zero-sum games. In a zero-sum game, for every strategy profile, the sum of the payoffs for the two players is zero, as the name suggests. So if one person is gaining, the other person has to be losing. So this game here is zero-sum. So matching pennies is zero-sum. This is not zero-sum. Zero-sum games are what we often think of when we think of games, not in the context of game theory, but in sort of just plain language. When we think of game, we think of a zero-sum game. Obviously, every zero-sum game is perfectly competitive, but not vice versa. So if you think of this as a Venn diagram, you've got the set of all possible games. Among those, you've got perfectly competitive games, and among those, you've got zero-sum games. Now, if we go back to our definition of security strategies, it's pretty clear to see that because the preferences over the outcomes are diametrically opposed for the two players, that if you have a Nash equilibrium of a perfectly competitive game, then you don't have to be paranoid to think that the other player is out to get you, because they are out to get you, because the best thing for them is the worst thing for you. So intuitively, it becomes very clear that you have the following result. It says that if you have a Nash equilibrium of one of these games, then each player has to be playing a security strategy. And you can make a similar statement about max-min strategies if you find a mixed strategy Nash equilibrium. The textbook goes through a careful proof of this statement. You should go and read that. But I've given you the intuition for why that's the case. So it should be easy for you to follow the math in the textbook.